It's a pleasure to give these lectures here. I wanted to encourage the students to, encourage everybody in the room to ask questions whenever there is anything unclear or dubious or anything that I could try to explain again. So interrupt me please as much as you like. Though I've provided a very long and formidable syllabus, I don't think I'll possibly be able to cover all of it. So I'm not in a rush, and we can spend as much time discussing some topics, whatever you like. So the plan for today is that I'll cover some material which is pretty basic, but it's not usually covered in courses on quantum. It's not usually covered in courses on quantum field theory. The material today is about how quantum field theory historically arose from classical statistical systems. And then I'll also get to a little bit more modern stuff about how quantum field theory arises from quantum phase transitions. So this is a little bit of a historical thing. And this is a more modern subject, which is still developing quite steadily. And I will emphasize today various constructions in statistical physics and in quantum phase transitions. These are zero temperature. So these are this is zero temperature stuff. So I'll emphasize today various constructions which lead to Landau-Ginzburg models, which are especially simple kinds of quantum field theories. And the purpose of these lectures is to prepare the ground as we go along to more sophisticated things, what is called beyond Landau-Ginzburg, where you will encounter much more modern ideas about phase transitions and quantum field theories that have to do with topology and things that are much more modern. But first I'll start with some basic stuff to make sure that everybody is on the same page. Okay, so if there are any questions, just interrupt me. You don't have to raise your hand, just feel free to interrupt me whenever you want. So really the most, historically perhaps, the most familiar example and also the one that had the most impact on the early developments of quantum field theory is the classical Ising system. So this is some classical statistical Ising system, which is something of the following sort. So you take d dimensions. Here, this is a classical statistical system, so there is no time. This is purely Euclidean. And you imagine, you just take a lattice in d dimensions. I'll just draw a two-dimensional lattice for lack of drawing skills, but you should imagine a d-dimensional lattice. And you just assign, and so at every point on this lattice, you say that there is a binary variable which is either -1 or 1. So this variable is called Si, and this variable Si is either -1 or 1. So it's a purely classical system where you put a binary variable at each point on the lattice. And so there are many configurations that are possible. You can put there are many configurations. This lattice could be in some large finite volume or infinite volume. And then you just say that each configuration has the following energy. It's a -J, where J is the only dimensionful scale in the problem, and it has dimensions of energy. And the minus sign here is important. And then you just say that you take Si and you multiply it by Sj, where I and J are neighboring sites. So this notation with the triangle in the sum will denote throughout this course neighboring sites. So you sum over all the possible neighboring sites and you multiply these binary variables. And so for each configuration, you can then compute the total energy of that configuration. Now, it's important that this minus sign, people call it ferromagnetic. So the minus sign leads to the ferromagnetic Ising model. That's the terminology. And the reason that people call it ferromagnetic is that clearly to minimize this energy, one would like to put the same value of this variable on all the sides. So you would either put plus everywhere, 1 everywhere, or -1 everywhere. And so this leads to some sort of total magnetization. So it's like the magnets that stick on your fridge. They are in this kind of, they're similar to this model. Okay, so what does one do? One then constructs the ordinary Boltzmann sum. So one studies the partition function, which is a sum over all the possible configurations. It's a sum over all the possible configurations with the energy functional divided by temperature. Okay? And clearly the answer depends only on J over T, since J is the only dimensionful scale. So this is some function of J over T and of space. So this is some function of J over T given some concrete lattice with some definite number of lattice sites. Okay, and a lot is known about this function of J over T. So people have computed it on the computer. People have found a lot of analytical results about this function. And for my purpose, the most important thing that I would like to explain about this function is that there is a critical TC, which depends on the number of space dimensions. And this TC is some function of J. So, and the number of dimensions. And that TC, so C stands either for Curie or for critical. So C, you could call it the Curie temperature after Marie Curie, Curie temperature, or a critical temperature. So C stands for either Curie or critical. And at this critical temperature, something rather amazing happens in the large volume limit. In the that's called the thermodynamic limit. So the thermodynamic limit is, by definition, the limit of large lattices or large volume, which is the same, or infinite lattice. That's a thermodynamic limit. So in that there is some temperature Tc at which something very special happens in the thermodynamic limit, and this is called the phase transition. There is a second order phase transition. I'll explain what it means. There is a second order phase transition, and this is true in all dimensions d which are bigger than 1. I'll discuss what happens in one dimension later. So there is something rather special, something special happens at some concrete temperature Tc, Curie temperature, and people have been measuring the properties of this critical temperature for ages, and they are what people have been doing is to characterize the behavior of various interesting physical quantities as the temperature is taken close to Tc. So as we take the temperature to Tc, experimentalists would characterize the behavior of the system, which is very special. This is the second order phase transition, by a bunch of different quantities that they measure. So there are 6 or 7 very famous quantities that people measure, which are the heat capacity, magnetization, magnetic susceptibility, some 2-point function that I'll explain in a second. These are some quantities that people measure. The correlation length, And well, let me see. How many do I got? 1, 2. So we have 1, 2, 3, 4, 5. Yeah, I think that's all I wanted to cover. Okay, so what people have observed? There should be 6. I'm missing one, or I'm not counting correctly. Let me just see. I'm missing one quantity that... yeah. There are 2 notions of magnetization that I'll explain. Okay, so the heat capacity is the classical definition is how much energy do you need to pump into the system to change the temperature by some amount, or in other words, by changing the temperature by some amount, how much the energy density changes. Okay, and people have observed that as you take the temperature to be very close to Tc, this has a singular behavior, which is characterized by some exponent alpha, which is positive typically. So the heat capacity itself is typically typically behaves in this non-differentiable fashion where alpha is some fractional number. Then there is the magnetization. The magnetization is the average number of spins pointing up minus the average number of spins pointing down. And as you take T closer to Tc from below or from above, there is some kind of singular behavior with some new exponent that is called beta. Another thing you can do is that you can put something like a magnetic field that would align the spins at 0 temperature in the same direction. And you can ask at Tc, how does the system react to such a magnetic field? And let's call this magnetic field H. Then this also behaves in some slightly non-analytic way, like H to the power 1 over delta, where H is the external magnetic field, which in the energy functional appears like H times the sum over the spins. Okay, so you could try to either put H to 0, like here, and just change the temperature, or you could try to put T equals Tc and change H. These are 2 experiments that people do. Then there is the magnetic susceptibility, which again behaves in a singular fashion with some exponent that's called gamma. And then there is a 2-point correlation of the magnetization. So here M is the total magnetization, but here I'm abusing notation a little bit. Here M is the local magnetization. So you take some large number of sites, let's say 100 sites, you divide it by 100, and you measure the average magnetization in that area. And then you ask you just sum over all the possible configurations. So there is some sense of typical configurations. And you ask what is the correlation of the magnetization in one area and another area. That also defines some exponent, which is 1 over the distance. And then people conventionally put d, where d is the number of dimensions, minus 2 plus eta. So this defines the exponent eta. And finally, there is perhaps the most important quantity, which is called the correlation length. And this is the typical scale in units, in lattice size units, over which you see correlations between different areas in this lattice. And this goes like T minus Tc to the power minus nu. And very importantly, in this kind of experiments, nu goes to infinity. Nu is positive. This is perhaps the most important thing to remember, because what it means, this gives you the intuitive explanation for what's going on at this critical temperature Tc. At this critical temperature Tc, there are correlations over long distances. So in some sense, the lattice sort of, in some sense, disappears. That's the first intuition for the emergence of a continuum description. The emergence of what we call quantum field theory is that near the critical temperature, the correlations span over so many lattice sites that in some sense you can forget about the lattice. So that's the first intuition, that we can forget about the lattice if we're very close to TC, since the correlation spans so many lattice sites. Okay? So that's the first idea that historically. Okay. Now, all these 6 experiments that I described, they seem completely independent of each other. And people went on for many years, and they measured these exponents, alpha, beta, gamma, delta, nu, and eta. They were measuring these exponents. But then the experimentalists have observed that in all the experiments that they were doing on this model and also other models, there were relations between these exponents. There were all kind of linear relations between these exponents. These are called hyperscaling relations. Hyperscaling relations. So these are experimental relations between the 6 different Greek letters, which take the following form. I'm just going to write these relations to impress them upon you. So these are like mysterious-looking relations between completely different experiments. So alpha plus 2, beta plus gamma equals 2. Gamma is beta times delta minus 1. And gamma is nu times 2 minus eta. And mu date is 2 minus alpha. Okay, so if you're an experimentalist, this looks shocking, right? These are completely different experiments. And then you discover these mysterious relations, which hold to many digits. And they reappear in many other experiments too. These hyperscaling relations. So this is a mystery of why are there 4 relations between 6 different experiments. And the explanation of these relations comes from this idea that you can forget about the lattice, pass to some continuum description, and in this continuum description there are more symmetries. There are more symmetries because in the continuum description we don't have a lattice, we have translational symmetry. In the continuum description, furthermore, the fact that the correlation length is infinite leads to some sort of scaling symmetry. Okay? So the emergence of the continuum description is very important to explain these experimental relations. Let me show you how the continuum description explains these relations abstractly, and then we'll talk about the actual continuum description for this model. Are there any questions so far? Okay. So the idea is to try to pass to a continuum description. So continuum description near TC. So when T is very close to TC, a continuum description should be a good approximation. So what are the symmetries that we expect from the continuum description? Remember that this is a Euclidean theorem. There is no time, and there is no dynamics. It's just a continuum model that replaces these discrete spins by something else, which is a function of space-time. So what are the symmetries that we expect? Anybody has a suggestion? Any symmetry that you might expect from this continuum description? I didn't hear. Yeah, there is all the Euclidean symmetry, the whole Euclidean isometry group, which includes rotations in d dimensions and translations in d dimensions. Yeah, this is the Euclidean Poincare group. And in fact, that's all you are allowed to expect when T is close to TC, but not quite equal to TC. The big discovery, or the big additional input into this subject, came from a deep realization I think from the Landau school, if I am historically if this is, I think it came from the Landau school, if I remember correctly, which is that at exactly t equals tc, there is an additional symmetry. So not at t equals, when t is very close to tc, you still have a continuum description with Euclidean symmetry. But when t is exactly equal to tc, the continuum description acquires an additional symmetry. Anybody has a guess what it is? No, Landau didn't know about conformal symmetry. That came much later. Scaling. So Landau's theory stems from scaling symmetry, where lambda is positive. You could take lambda to be negative, but that might be parity. He didn't talk about. I mean, you could take lambda to be whatever you want. Let's say any real number. In this instance, there is also parity, so it doesn't matter. So xi goes to lambda, where lambda is any real number. So Landau did not know about the conformal symmetry, but he realized, or I don't know who, realized that there is this symmetry at t equals to c. Okay. Now, realizing that there is this symmetry is crucial to explain these four relations. Let's see how that comes about. So the way this comes about is that let's denote the generator of the symmetry by D for dilatations. Dilatations. So now, if you have now in this continuum description, there are local operators. I put a hat even though we don't have a Hilbert space interpretation. It's just Euclidean theory, but I just put a hat for the sake of it. So these are some local operators that depend on these space-time dimensions. Well, in the days, they wouldn't call them local operators. You could just think about them as combinations of the some functions that depend on space, some composite fields. You could just think about them as composite fields. So we know how composite fields transform under the Poincare group, right? If you translate x, that's like translating the argument, which is the same as putting derivatives in front of this composite field. Or if you were to rotate, then you would rotate the argument, plus if this composite field has vector indices, you would also rotate these vector indices. But now you gotta say what happens to this composite field when you make a dilatation. So you have to say what is the commutator of this composite field with dilatations. That's the thing that the Landau school people did. They realized that you have to say what this commutator is equal to. Of course, they didn't talk about it in the language of commutators. There was no interpretation of a Hilbert space. So if you don't like it, we can also think about it as just a question of what does the dilatation do? Dilatation of OX do. What does it do? So what you realize is that, of course, you have to dilatate the coordinate. You have to put lambda x. But there could be a prefactor. There could be a homogeneous scaling of this operator. In fact, it could be more complicated. You could mix, various operators could mix. But just for simplicity, you just write this. And delta is a feature of O itself. Okay? Delta is some parameter that could be any real number. And it depends on O. So different O's could have different deltas. So delta of O, that's what we call the scaling dimension of O. Okay? Okay. Now, this fact leads to really interesting constraints on two-point correlation functions. So if you have an operator O at n and an operator O at 0, then using Poincare symmetry, it can only be a function of the distance. Let's say that O are scalar operators, so they have no vector indices. So it must be only a function of the distance squared. But the existence of this additional dilatation symmetry fixes the function completely. So there is only one function of the distance that you allow to write, which is 1 over the distance to the power 2 delta O. Up to some prefactor that can be set to 1 without loss of generality by changing the normalization of O in an X-independent fashion. Okay. So this is up to a normalization, which you can choose to be such that this is true. So this symmetry is really powerful. It fixes two-point correlation functions completely. In ordinary quantum field theory that does not enjoy dilatation symmetry, these two-point functions could be arbitrarily complicated, almost. But in this case, they're unique. Once you know this number, it's unique. Okay, the next step which these people did, is quite remarkable conceptually. So I told you that the phase transition arises when you tune the temperature to be the critical temperature Tc. But also I told you that there is a magnetic field which we put to 0 in most of these experiments to go to the to dial the system into the phase transition. We put this magnetic field to 0. So what they've realized is that suppose you have some kind of well, I just want to make a small detour. That will not, I just want to make a small comment before I go to the next step to explain these hyperscaling relations. What I wanted to say is that historically, just to complete this historical survey, much later, 30 years after this work of the Landau School, in the 1970s, people have conjectured, and in many cases also tested this conjecture, that in fact the symmetries are even bigger at Tc. So people have conjectured that at T equals Tc, the symmetries are even bigger, and they include the full conformal group. The conformal group is bigger than just the Euclidean group and dilatations. It has additional D conserved charges. It has additional D conserved symmetries. Additional D conserved symmetries, or conserved charges, which are called special conformal transformations, for those of you who might want to look them up. Okay, those Landau did not know about, and it was not important for what he did. But they're very important for other applications, which we will not discuss. Okay, so for this reason nowadays, at T equals Tc, we call this a conformal filter, since it enjoys the full conformal group. This conjecture was not really proven in full generality, but everybody believes it's correct. So what they realized is that we should think about it as a conformal. So we have a conformal field theory, which is the correct description of the system at T equals Tc and H equals to 0. But then, as we change the magnetic field and we change the temperature, we should add some local operators to the action. Okay, this is the big next step. However, they did a little bit more than that. They realized that they could change the temperature as a function of space. So we don't have to raise the temperature uniformly in the whole system. We may raise the temperature a little bit in some chunk of the lattice, and not in another chunk of the lattice. And similarly, we can put a magnetic field in some space, in some part of space, but not in another part of space. So the idea is to add to the action an integral over x. This is very important. We integrate over the whole lattice, and then we have T minus Tc multiplying some local operator, which is called the energy operator, because it couples to the small change in the temperature. So this is some function of x. This is some, let me just put explicitly the x dependence here. So we have T of x minus Tc times O of x. This is some operator. And a similar piece for the magnetic field. This is some O. So this operator is called the energy operator in the literature, just because it couples to temperature. So people call it the energy operator. It couples to changes in the temperature, and changing the temperature changes the local energy density. And this is called, sometimes the spin operator. There are several names for it. So this is called the energy operator, and it's often denoted by epsilon. And this is called the maybe spin operator. And now the claim of the Landau school, which was only justified years after, is that to understand all these high experiments of heat capacity, magnetization, blah, blah, these are the only two operators we should care about. So you could say that you don't understand why. For instance, changing the temperature a little bit could couple to many operators with different scaling dimensions. Who said that the only operator that we should add has a definite scaling dimension? So the idea is that this operator has some definite scaling dimension, which is called delta epsilon. And this one has some definite scaling dimension, which is called delta sigma. This is a huge assumption. There is no reason whatsoever to believe that changing the temperature locally, even by a small amount, would couple to one operator with a definite scaling dimension. In fact, it's not even true. But years later, the work of Wilson justified this assumption. Wilson argued that the things that you threw away, like all the other operators that could be generated, do not affect the scaling, do not affect these experiments. Okay, so this was later justified by Wilson, essentially. What did Wilson say? Wilson said that to understand these experiments, which are about this heat capacity correlation lengths, we should only keep track of the operators of the lowest possible scaling dimension. And more generally, only those deltas that are smaller than d. This is what we call now relevant operators. That's why they're called relevant, because the others are irrelevant for these experiments. So Wilson gave a scaling argument for why the other operators, whose deltas, which are a priori unknown numbers, if they're bigger than d, we throw them away. And we should only keep those that are smaller than d. So, therefore, the idea is that you can compute all these things from just the delta of epsilon and delta of sigma. And that's it. That explains why 6 different experiments have 4 relations, because these Greek letters depend on 2 parameters. So 6 objects that depend on 2 parameters ought to obey 6 relations. And you can write explicitly how it goes. I can even do one example. I'll do one example to show you how you make the transition between experiment and this abstract theory. So we can do one example, let's say, which is the easiest. Let me see. Yeah. There is this one. Yeah, so first they realized that there is a continuum description should apply, because you saw that the correlation length captures many lattice points. So you could maybe forget about lattice. Okay? To actually justify it mathematically is not trivial. And in fact, it's an open problem. The fact that quantum field theory is the correct description, correlation length is very large, it's a plausible conjecture, but nobody proved it. This is more or less equivalent to proving that quantum field theory exists. And nobody has ever done that. Regarding your other question, when the correlation length is infinite, you might think that the system looks the same at every scale. Since the correlation length is infinite, there is no inherent scale in the system. So the correlation length is essentially the only scale in the system when the correlation length is very big. So when it goes to infinity, there is no other scale that's inherent in the system. And so you might be tempted to say that, therefore, the system looks the same at all scales. I mean, also these power laws, when you see power laws mean that there is no inherent, because when there is an inherent scale, you might get exponents. Power laws suggest that there's some kind of scaling symmetry. Okay. Okay, so let's do one example, which well, let's try to understand this formula. So you remember that the correlation length, it was here, the correlation length explodes when you take the temperature to be very close to Tc, like minus Ni. And in terms of these two scaling dimensions, you can give an expression for Ni. So let's do that, see how it works in one concrete example. So this should be some function of these scaling dimensions. So let me show you how it works. It's the same trick. Using the same trick, you can do it for all the 6 Greek letters. And this is a very nice homework exercise. If you have extra time, you can try to do the rest. I'll do one and you'll do the rest. So the idea is that we look at this formula. We look at this formula closely and we realize that this formula breaks the dilatation symmetry. Why? Because what is the dimension of this thing? How does this scale with dilatations? By definition, the dimension of this thing is delta epsilon. And this is some number, which I'll quote later. It's known experimentally. But this number is some number that's smaller than d. Some number that is known to 5 or 6 digits and is smaller than d. So this is some known function of space and time. You decide what the temperature profile is. Nobody tells you what it is. You decide what this function is. So this addition to the action breaks the conformal symmetry explicitly. So this explicitly breaks conformal symmetry. Or dilatation symmetry. But then there is a cool idea which is called the Spurian analysis. It's an idea that is applicable in many, many areas of physics, and everybody uses it all the time, which is that even though this breaks conformal symmetry, if we sort of mentally assign to this external function dimension d minus epsilon, d minus delta epsilon, then this would formally preserve conformal symmetry. Of course, this makes no sense because this is a function that you choose, so you cannot rescale it. But the idea is that all the formulas should be consistent with this object appearing as if it had that dimension. Is that clear? Is that clear? Or should I try to explain it with another example? Anybody clear or not? It's not clear. This is a very deep idea that people use in many. Let me just give you an example. It's very important to understand this idea since it's widely applicable in many areas. This idea is called nowadays Spurian analysis. There is an example that I like to use to explain this idea, which is that the hydrogen atom. So this is something in quantum mechanics, okay? Quantum mechanics of undergraduate. Sorry, this is an example from quantum mechanics of undergraduate quantum mechanics. Let's suppose you have a Hamiltonian for a particle that's moving in a centrally symmetric potential, like 1 over, something like 1 over r. E squared or something. Doesn't matter. So the energy levels of this particle are known to you. And furthermore, there is a symmetry in this problem, which is SO3. SO3 is a symmetry, right? So SO3 is a symmetry. And you know that the wave functions have to sit in representations of SO3. And the energy is a function of some index n. And it cannot depend on it commutes with SO3. So if you take a state, you apply SO3, you get the same energy. Is that true? That's known, right? Now, what if I added an external electric field? Is there still SO3? No. The SO3 is broken by the God-given or experimentalist given choice of the direction of the electric field, right? But does it mean that we completely lose our ability to use SO3? For instance, if I ask you about the energy levels of this, the energy levels of this system, would you not agree that they're only functions of E dot E? So if somebody plots the whole set of energy levels, can they depend on anything other than E dot E? Can they, for example, depend separately on EX or EY? No, they can only depend on this combination E dot EY, even though SO3 is not a symmetry, because we can, in our mind, assign to this external parameter SO3 transformation properties. It transforms like a vector under SO3, and then we can still use SO3. Right? So as external parameters can be assigned formally transformation properties under broken symmetries, and then final answers to physical observables can only depend on SO3 invariant combinations of these spurious symmetries. Is that clear? So the same deep idea can be applied to conformal invariance. We assign this external God-given function formal scaling d minus delta, and then physical quantities can only depend on conformally invariant combinations or conformally consistent combinations of these external parameters. So in particular, the correlation length, it's something that has dimensions of length. So how does it transform under x goes to lambda x? It transforms like 1 over lambda. So this is an object with dimensions of length. And therefore, if it's got the correlation length has to be infinite at t equals tc. But when t is not tc, then the correlation length spans many lattice sites, but it's not infinite. And the physical question is, what is the correlation length as a function of t minus tc? So we can use this spurious symmetry to say that it can be some factor that we cannot compute. The prefactor is extremely hard to compute. And in fact, I think it's not something that I actually know how to do. But the scaling with t minus tc is very easy. It must be just 1 over this. Or with a minus sign, sorry. So this has dimensions d minus delta. This has to have dimensions minus 1, so it has to be minus 1. And that's it. So the scaling with the temperature is known from spurious conformal symmetry. But the prefactor is extremely hard to compute. So from this, we find, using that definition, for the definition for nu was that the correlation length goes like t minus tc minus nu. So therefore nu is 1 over d minus delta epsilon.
Sorry, but how do you know that the behavior of the correlation? I didn't get the argument why, the spurious analysis, yes, but I don't know why you could conclude that this is the behavior of the correlation length near the...
Oh, it's because if you do a rescaling of space, correlation length is like a length. So it transforms like a meter. So if you do x going to lambda x, xc goes to lambda xc. So you have to cook up a combination of these things that would transform in the same way under x going to lambda x. And this transforms with this dimension, so therefore this has to be the right answer. So you just cook up something that has dimension minus 1. Mass has dimension 1, length has dimension -1, this has dimension d minus delta. Using similar arguments, you would be able to redo all the other quantities. Okay? So let me just tell you the experimental values, just to impress it upon you that we actually know these things from many years. So let me just go over the examples. So we have d equals 1, d equals 2, d equals 3, and d bigger or equal to 4. So let's start from a one-dimensional lattice of spins, of plus and minus ones. Does anybody know what happens in that case? There is no phase transition. The correlation length is always 0. There is no second order phase transition. This is called Landau theorem, that there cannot be phase transitions in one dimension for classical statistical systems. It's a general theorem about classical statistical systems, that there cannot be phase transitions in one dimension. In fact, this system is exactly solvable in one dimension, and you can do it at home and see that there is no such thing as TC in this system. There is no, okay. In d equals 2, this model was solved by Onsager, and he found that delta epsilon is 1, and delta sigma is 1 over 8. Nice rational numbers. Well, it's a special temperature at which the heat capacity has this non-analytic behavior. The correlation length has a non-analytic behavior. It's a special point. It's a special temperature TC at which quantities behave in a singular fashion in the thermodynamic limit. Now, I said the word thermodynamic limit, and maybe some of you don't see why this is important. But the whole thing is about the fact that the correlation length goes to infinity. So if you're on a finite lattice, this will never happen. There is no singularity on a finite lattice because there is no space for the correlation length to go to infinity. It's really, you really have to be thinking carefully about the large volume limit because the whole thing is about this divergence of various quantities because of the correlation length going to infinity. So it's really important to take the large volume limit first, not second. Okay? So you always imagine that the volume is the biggest parameter. Now, in d equals 3, we do not have a solution like Onsager's. So we do not have closed form formulas for these numbers delta epsilon and delta sigma, but they've been computed by Monte Carlo simulations, by what's called the conformal bootstrap, by experiments, and they're known to several digits. So I'll just quote the first few digits. So we know that delta epsilon is 1.413, and delta sigma is 0.5182. Probably these are some transcendental numbers, but I just wanted to emphasize that these are like constants of nature. These are not some made-up objects. These are constants of nature that are canonical constants of nature. It's like pi. It's like an important transcendental number, probably, that we don't know. Okay. And for d equals to 4 and up, I will explain in a few minutes that actually delta epsilon is just is d minus 2, and delta sigma is d minus 2 over 2. These formulas might seem familiar from quantum field theory courses. This is called mean field theory. MFT, mean field theory. So this model is in the mean field theory universality class for higher dimensions, for d equals 4 and above. Okay?
What makes three-dimensional?
Say again.
What makes the three-dimensional?
Actually, people can formally extend this problem to any number of dimensions, even fractional dimensions. And the problem is interesting in this whole range. So between 2 and 4, the problem is interesting, not solvable. And at 4 and above, it's trivial. This is the solution. It's mean filter. And at 2 and below, it's kind of trivial. You will see a continuum quantum filter can explain why this is the case. So you'll see an explanation soon. But yeah, at this stage, it appears somewhat mysterious. Okay, so now let me, yeah. Say again?
In the mean field theory approximation, when you compute these exponents.
No, I'm not an approximation. This is properties of that model. I'm giving you the exact properties of the Ising model. I'm not making any approximation. These are the properties of this model. Exponent of minus s dot s. These are the exact properties of this model. I'm not making an approximation. Okay? You'll see an explanation from quantum field theory for why this is true. Okay. Any other questions about this? Yeah.
One makes some sort of large n limit in 1D to still have phase transitions.
What is n?
Have some large number of degrees of freedom for lattice size to compensate the fact that you have small different space-time dimension to allow for phase transition. Sometimes one does this, like taking the large n limit.
Oh, you're asking if, like, instead of the spin having values -1 and 1, maybe there could be many different values, and you could make the phase transition even lower than 2. Yeah, you can definitely do that, in principle. Yeah. In fact, well, I don't want to discuss it, but in systems where there are infinitely many degrees of freedom at every point, you can even have a phase transition in 0 dimensions. Okay. Any other questions before I go to the actual quantum field theory description of this system? This is still all Euclidean, right? There is no dynamics and there is no quantum mechanics here. So actually the word quantum field theory is extremely misleading because quantum field theory doesn't have to be quantum. This is completely classical. So there is no H bar. So this is a confusing name. Okay. Quantum field theory is some abstract mathematical thing that allows to think about continuum systems with large correlation lengths, but it has nothing to do with quantum mechanics. In particular, in this Euclidean version, there is no Hilbert space, there is no H bar, there are no operators, there is no von Neumann algebra. Okay, so QFT is a confusing name. So the proposal, or if you want, this is a true fact, is that the quantum field theory that okay, so we're looking for some quantum field theory that describes the physics of the Ising system when t goes to Tc. If t is very far from Tc, there is no useful continuum description because the correlation length is typically one site, one lattice site. So if your correlation length is typically one lattice site, there is no continuum approximation. It's useless. Quantum field theory is a useful approximation when the temperature is very close to the Curie temperature, because then the correlation length is large and you can capture many lattice sites, and you can use a continuum description. It's like there is in mathematics, there is discrete mathematics and there is continuous mathematics, calculus. Calculus is sometimes a good approximation to discrete mathematics, but not always. There are some problems in discrete mathematics that have no calculus interpretation. So lattice systems are like discrete mathematics and quantum field theory is like calculus. And of course, calculus is much more powerful. So t going to Tc. So when t is going, so more precisely, it's when t minus Tc over j is much, much smaller than 1. This is what you want to do. right? In this limit, the idea is that this is described by d phi squared plus m squared phi squared, where phi is a real continuous field, plus lambda phi to the 4 plus ta 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 ta. Well, you can also put a magnetic field, sorry. I'll put a magnetic field, h phi plus lambda phi to the 4. Ta ta ta. So this quantum field theory has potentially infinitely many parameters, but one throws away everything past this point because they have a higher power of phi to the 4, and from Wilson's logic we know that higher dimensional operators do not affect long distance physics, so we throw them away by Wilson's general paradigm that we should not keep infinitely many terms in quantum field theory because they do not contribute to long distance observables. But there are still parameters here, lambda, h, and m squared. I'll discuss them one by one. First of all, m squared is given up to an unknown coefficient that's very hard to compute by t minus tc with this convention. So there is it's positive. So there is a plus here. That's very important. H is proportional to h. And lambda, I'll put it to 1. But I could put it to 1 for some, it would be a little bit too schematic. So I'll just leave it for now. And you'll see that lambda is not really a parameter. You'll see in a second that lambda is not a parameter. Even though it looks like a parameter, when you go to the long distance limit, it's not a parameter.
Usually with certain approach, right, if I have to keep all the operators up to eventually.
Yeah.
And compatible with the symmetry.
Yeah, so I will argue soon that lambda is not a parameter, it flows.
And what about the cube?
Yeah, I have, this is a good point. You should also put phi cube. And that his coefficient will depend in some way on t minus tc and the magnetic field. You should put phi cube. I was a little bit too sloppy about it. It's actually important for some applications. So the reason that you throw away phi to the 5th and phi to the 6th is that, as I said, this is not a parameter. I'll explain why soon. And it flows to some fixed point. And at that fixed point, the other ones are irrelevant. Always, in all dimensions. So, okay, so let's try to understand. So this is some continuum quantum field theory. We're now on more familiar turf. So we can first understand the phase diagram of this quantum field theory. Let's put h to 0. Phi is a real field. So this quantum field theory has a Z2 symmetry where phi goes to minus phi. This is the continuum version of the Ising model symmetry where you take each s to minus s. That was the symmetry of the Ising Hamiltonian at vanishing magnetic field, and this is the continuum version. So one diagram that I like to draw, I'm now introducing it since this diagram will appear dozens of times through this course, is the phases of this quantum field theory as a function of m squared. By phases, I mean the long distance limit. What is the correct answer to the long distance limit? Correlation functions at long distances, number of vacua, massless fields, yes or no, stuff like that. So when m squared is huge and negative, this is around, let's say that this is where it's like 0, somewhere here. The notion of 0 is, I'll discuss it soon, but let's take m squared to be huge and negative. When m squared is huge and negative, you can use classical analysis. And you see that phi condenses, right? You have to solve the potential minus phi squared plus phi to the 4. There are 2 vacua. So here there are 2 vacua. Both of them are gapped. Gapped 2 vacua. Z2 is spontaneously broken. That's the answer at huge negative m squared. And you can see it classically because when m squared is huge and negative, classical analysis is valid. The classical analysis is valid. All right? Now, when m squared is huge and positive, similarly, you have just one vacuum, and you can establish it with your naked eye, right? Naked, it's gapped, and Z2 is preserved. So this allows us to explore the phase diagram of the statistical system near TC. Does that make sense? Yeah, that's exactly what happens in the Ising model. In the Ising model, below the Curie temperature, it magnetizes. That's why these magnets stick on your fridge. And if you go above TC, then you lose magnetism. As you heat up the system, you lose the magnetism. And there is one vacuum. So there is no more magnetic symmetry. There is no more aligning of the spins. The spins are not aligned anymore. So that's good. But you see, just from the quantum field theory point of view, there is a phase transition. So this quantum field theory at 0h must have some sort of phase transition. You cannot continuously go from this picture to this picture without something happening in the middle. So something must happen here. Yeah.
M squared is smaller than 0?
Yeah. Since there is a phi to the 4, the potential is still positive at large fields, and it's bounded from below. So there is no reason why m squared cannot be negative. In fact, as I argued, the map from the Ising model to quantum field theory is such that m squared is the same as t minus tc up to some incomputable constant. So for t smaller than tc, m squared is negative.
It's imaginary in some way. I'm just trying to think why square number.
When people write m squared in QFT, they don't mean that it's literally the square number, the square of a number. It's just the coefficient of phi squared.
Okay.
So you could say that, you know, like if you expand around the origin, it seems like there is a particle with negative mass squared. So that would be called a tachyon. But this is not actually the vacuum movement theory. The vacuum is here, and if you expand around the correct vacuum, there are no tachyons. All the mass squareds, all the physical mass squareds are positive. We should take a break after these two questions. Yeah.
So in reading, we assume that T minus TC is very small, right?
Yeah.
But
Yeah.
now m squared is more or less T minus TC, and now we can still take that to be large or very small.
Okay. So the quantum. So there are two. This is a very important question. So quantum field theory is a well-defined subject by itself. And you can study the phases of quantum field theory regardless of the lattice system. And the lattice is a well-defined subject by itself. You can study its dynamics regardless of quantum field theory. But there is some area here where they agree. This is the overlap area. To analyze this area, it's hard in quantum field theory because it's strongly coupled, and it's also hard on the lattice. But quantum field theory allows us to analyze these regimes and then make some conjectures about the rest. So you cannot really solve quantum field theory in this regime. Neither can you solve the lattice. But quantum field theory gives you another parameter, so to speak, or another perspective on the problem, which is completely in the continuum from the get-go. And it would allow you to make some sensible conjectures about what happens in this middle region. Yeah.
Yes, we wrote down in the effective action just up to figure 4.
Yeah.
But because basically we read the dimension from the classical action. What if I...
No, not yet. Yeah, that's right. Yeah, that's exactly what I'm going to discuss after the break, of why it's justified to throw away the higher powers and what happens near this region.
Yeah.
These two questions are very closely related, as you'll see. Is that what you wanted to ask?
Yes, I mean, I can trust somehow that this is a good answer because I am nearby after 2, but it works.
But
if
it's
I have a strong quantum correction, I cannot...
Right. Right. If you have strong quantum corrections, it's not a priori justified to throw away the higher powers. But I'll explain that in this particular system, it's strongly coupled in some regimes. But we know enough to be sure that it's okay. So you'll see it after the break. Any other questions before the break? Okay. Let's take a break now. So you have to get used to these pictures. I'm going to keep drawing these pictures of the phases of quantum field theory. So in this particular model where we put h to 0, we see that there must be some phase transition. So we see that on one side this quantum field theory has 2 vacua, and on the other side this quantum field theory has 1 vacuum, and therefore there must be some phase transition between the two, between the left hand side of the figure and the right hand side of the figure. And it's a very interesting question to ask what happens in between. So these are like where the dragons are, and we cannot necessarily solve this question analytically. But there are some cases where we can make a lot of progress analytically, which is that let's start by making a conjecture, and then you'll see that in some cases this conjecture can actually be retrospectively proven. Okay, so the conjecture is going to be that the phase transition between these two regimes of quantum field theory happens at exactly one point. This point where it's located is a little bit a question of taste, but in quantum field theory books we think about this point as m squared equals 0, but it's really somewhat of a question of taste. But think about it as m squared equals 0. So at this point, the model is just d phi squared plus phi to the 4. There is no mass squared. So let's just for a second make this conjecture that there is only one point where the transition happens, and at this point there is a conformal field theory. So we have to understand what conformal field theory does this model flow to. This is not a conformal field theory. For instance, in 3 dimensions, the dimension of phi is a half, and therefore the dimension of phi to the 4 is 2. This is not a conformal field theory. It's not even invariant under scalings. But it flows to a conformal field theory. How does it flow? Lambda increases, so the theory becomes more and more strongly coupled, and it stops at some conformal field theory. And how does that take place? Depends a little bit on the number of dimensions. So let's do the various cases. Let's try to understand this field theory. So this should be somewhat familiar from QFT classes. The fate of this quantum field theory should be familiar from QFT classes, but I'll review it nonetheless. So the naive dimension of phi to the 4, this is the UV dimension. This is the naive UV dimension. Is given by just, this is what they call sometimes the engineering dimension. This is the dimension of this perturbation in the ultraviolet around the free field theory. And that's given by 2 times d minus 2. Now the model flows to a strongly interacting model if this is a relevant perturbation. If it's irrelevant, it's just free field theory. If it's relevant, it flows to an interacting model. So for d bigger or equal to 4, this interaction is irrelevant, while d equals 4 exactly is a borderline case, and there you have to compute the beta function. So really, all this stuff about the beta function that you have learned in QFT is in order to decide what is the fate of this model at exactly d equals 4. Does it flow to strong coupling, or does it flow to free field theory? And as you remember, the beta function is positive in this model. It's what they call infrared free in QFT books, and this is therefore this flows to free field theory. Free field theory. So the fixed point at long distances. This model is not exactly free, but at very long distances it becomes free. Lambda goes to 0. So lambda flows to 0 at long distances, and the model becomes free. And for that reason, when d is bigger or equal to 4, this is true. The scaling dimensions of phi squared and phi they are what they are in free field theory. So that explains in a very beautiful way, through the continuum quantum field theory, why the Ising model behaves like mean field theory in dimensions bigger than 4. It's because the phi to the 4 interaction is infrared free above 4 dimensions. And that also explains why we didn't have to add phi to the 6. Phi to the 6 would be even more irrelevant than phi to the 4. Then there is d equal 3. Then there is d bigger than, then there is d which is smaller than 4. And then there is d equals 1. So let's do those. Okay? Okay, let's do those. When d is between 1 and 4, this is a relevant operator. So you start from free fields at short distances. You add phi to the 4, they become strongly interacting. And as you go, you coarse grain, you go to longer and longer distances, they become more and more and more strongly interacting. So if you want, the beta function is negative between 1 and 4 dimensions. So this interaction becomes stronger and stronger and stronger and stronger. And in fact, we cannot compute anything. So we don't have analytical tools to compute anything between 1 and 4. With the small exception that if you're just a little bit before 4, a little bit below 4, like 3.99 dimensions, there is a technique that Wilson and Fisher developed, which is called the epsilon expansion, which allows you to understand in some details the long distance limit of this theory at 3.99 dimensions. But if you want to understand what happens at strictly 3 dimensions, we don't have a way to do that, because this interaction becomes stronger and stronger and stronger, and we cannot do anything. It's a non-perturbative thing. But we all believe that it flows to a conformal field theory, a non-trivial conformal field theory with some funny scaling dimensions, which are actually very far from the free field values. So you can see already in this answer, you could have seen a hint that this is a very strongly coupled field theory, because the engineering dimension of phi squared is 1. And you see that the actual answer is 1.4. So it's like 40% more than the free field prediction. So it's completely off. It's a strongly interacting system, full-fledged strongly interacting system. So the mean field theory value is d minus 2. That would have been 1. So this is CFT, and it's strongly coupled in general, with the exception of 3.99 dimensions. That's one exception. And the other exception is exactly 2 dimensions. In exactly 2 dimensions, Onsager somehow solved this model. Well, not exactly the field theory. He solved the Ising, the spin model, and he found the answer. It's analytically. Okay. Finally, d equals 1. D equals 1, all of you should know. This should explain why this statement that I made here, that there is no transition. What happens in d equals 1? Let's draw this diagram again. Here, we're studying it's quantum mechanics. D equals 1 is quantum mechanics, so you should feel in your own turf. So here, we're studying a potential in quantum mechanics, which is like that. And here, we're studying a potential in quantum mechanics, which is like that. In quantum field theory, this leads to 2 vacua. But in quantum mechanics, with this potential, how many vacua are there? 1. Why? Because there is an instanton in quantum mechanics that lifts the degeneracy. In quantum field theory, this doesn't happen. As soon as you have infinite space dimensions, so d bigger than 1, this doesn't happen. There are super selection sectors, and there are actually 2 vacua. But in quantum mechanics, there is no space, in some sense. There is only time in the Hamiltonian interpretation. And so there is this instanton. So the reason that I said that there is no transition is because in d equals 1, there are instantons. So Landau's theorem about classical statistical systems have a very nice weak rotated proof that this is quantum mechanics, if you think about this one direction as time. And in quantum mechanics, there are instantons. So there cannot be vacuum degeneracy. Okay, so Landau's proof, if you weak rotate, is 1 line. Landau's theorem, if you weak rotate, is 1 line. So between 2 and 4 dimensions, between 1 and 4 dimensions, it's a very tough problem. Yeah, here it's a very tough problem. And we cannot prove analytically that this picture is correct, but that's what we believe, and it's supported by a lot of lattice computations, Monte Carlo computations. It matches nicely with the Ising story, and the CFT is strongly coupled. For instance, this version of the CFT is very interesting in the numerical bootstrap community. Okay, so that's the story. That's the simplest nice example that exhibits many interesting features. You see the quantum filter side. You see the discrete lattice side. There is some nice correspondence. There are some nice conjectures about this phase transition. And now I can also go back to your question about why we don't add phi to the 6. So this is a very detailed question. You could say that here it's strongly coupled. How do I know that phi to the 6 is irrelevant? Well, lattice computations and the bootstrap have shown that the dimension of phi to the 6 is called in that community the epsilon prime dimension, and it's bigger than 3. They have just shown it numerically. So for that reason, you can ignore phi to the 6. There is no way I can prove it to you, but it has been shown numerically that the dimension of the next scalar operator, namely phi to the 6, is irrelevant. So that self-consistency justifies the whole picture. Any questions? Okie dokie. So we can continue. I wanted to mention now a generalization of this model that somebody already asked about. There is an interesting, before I go to the Hamiltonian version, which is more interesting, it has to do with quantum mechanics. I want to mention two facts. One is universality. Universality. And the other is scarcity. These are two important principles. Is this the right spelling? Scarcity. Yeah. These are two important principles that explain a lot of phenomena in nature. The universality is what I already explained, that when we couple T minus Tc to operators, we should not care about anything other than the leading operator with the smallest scaling dimension, because the others are irrelevant. And this is true everywhere between 2 and 4 dimensions. It's true everywhere between 2 and 4 dimensions. That explains why different lattice systems. So you could ask, what if I took the Ising energy S dot S and I added something like S dot S dot S dot S linking 4 nearby sites? You could ask, does this model behave completely differently from the other model without this interaction? And the idea is that these things would typically modify the answer by only irrelevant operators, because there are just 2 relevant operators in this fixed point. At this CFT, there are just two relevant operators, namely epsilon and sigma. And so these kind of things would maybe change the system by irrelevant operators, and so it wouldn't matter. So lots of lattice systems exhibit the exact same second order phase transition with the exact same critical exponents, alpha, beta, gamma, delta, nu, right? So if you measure alpha, beta, all these critical exponents, or you measure delta, epsilon, delta, sigma, they'll be exactly the same. Because the conformal filter is a rigid structure, which, it's like a Lie group. So these things are connected. Lie groups don't have continuous parameters, and conformal filters typically don't have continuous parameters. So once you find one, many models which have the right symmetries will basically go to that fixed point because they have no choice. So universality is the statement that if you added irrelevant operators, it would not matter. And scarcity is the statement that these things are isolated. They're like Lie groups. So they don't come in continuous families, they come in discrete families. And therefore, many models would have the exact same critical exponents. Are these two? These are different. No, scarcity and universality are different ideas. Universality is the idea that adding irrelevant operators would not change the critical exponents. That's the statement that I can drop phi to the 6, I can drop phi to the 8, blah, blah. Universality is the idea that these things are discrete, isolated. The conformal filters do not come in continuous families. So you cannot continuously change this parameter and have a consistent conformal filters. Conformal filters are typically isolated. And therefore, many models would inevitably be described by the same conformal filter. Is that clear? So these are not the same, but related ideas. So in particular, one very amusing fact is that if you look at boiling water, is boiling water quantum or classical? It's a classical system. This is the phase diagram of classical boiling water. Classical H2O, okay? So there are several phases, but in particular there is a let me get it straight. I want the liquid phase to be, so the gaseous phase will be here, and the liquid phase will be here. So there is a line that separates the liquid and gas phase, and then there is the icy phase. But in particular, this line ends. I don't know if you remember that, but vapor and water are not fundamentally different. There is a phase transition, of course, at room temperature and room pressure. So room temperature and pressure could be somewhere here. This is 1 atmosphere and 100 degrees Celsius. So there is a phase transition between water and vapor at room temperature. But if you went to much higher temperatures and much higher pressures, actually there is no phase transition. So you can just go around continuously. There is no latent heat, okay? And so this is a second order point. This is a first order line, this is second order. And guess what? The water at that point is described by this three-dimensional Ising model. Okay? So here we have D equals 3 Ising model. Is this surprising? No, because the conformal filters are scarce. If you have a system which has two relevant operators, it's gonna be this one. There is no choice. Okay? And there is nothing quantum about it. This is a classical phase diagram of water and vapor. And it's described by quantum filtering. Okay, so now, yeah?
This example, the two relevant operators operation.
Exactly. So there is one amusing thing about it, that indeed water has two relevant operators, pressure and temperature. One amusing thing about it is that there is no Z2 symmetry in water. In the Ising spin system, the Z2 is manifest throughout. But here, actually, the Z2 is approximate. So it's at this point, there is an approximate Z2 at long distances, but there is no Z2 in the microscopic theory of water. So the mapping between this pressure and temperature so there is a mapping between pressure and temperature of the water to m squared and h. But this is not, like, the mapping is complicated. But there is some mapping. So this region can be mapped locally to this region, but the mapping is complicated. Anyway, basically any system with two relevant parameters would be described by the same scarce CFT. Now there is a generalization, an interesting generalization that I just want to mention in passing, and then we'll discuss the deeper idea about connecting to quantum mechanics. So I want to mention in passing, this will be very important later, so I'll just mention it for now. There is an interesting generalization of the model that we just discussed, where phi is a vector, like phi 1, phi n. Somebody asked about putting many degrees of freedom at the same site. So an interesting generalization of the model that we just described is this. Integrated over the dx. Okay. This is a natural generalization of the model that we just studied. It has a lot of connections to statistical physics. It has a lot of connections to various phase transitions that are encountered in nature. And it's called the ON model. So this is the name of this model, the ON model. It has interesting phases, interesting conformal field theories, huge story about it. We'll encounter some special cases as we go on. They appear in some unexpected places. The reason that I wanted to mention that is that the three-dimensional Ising model is a strongly coupled theory, where this delta of epsilon and delta of sigma cannot be computed at the moment for principles. You can only compute them numerically. But in this, if you do this generalization, the infinite n limit is actually exactly solvable, and delta of phi squared is given by 2, and delta of phi is by 0.5. So this is some kind of extrapolation of the Ising model that can be solved analytically in 3 dimensions. I just wanted to mention it for your, if you've not seen it before, for your general education. Okay, so now we get to the deeper idea of a... Oh, and another thing is that this class of models is called Landau-Ginzburg. I want to say a few words about it. What is Landau-Ginzburg? These are called Landau-Ginzburg models. Now, Landau-Ginzburg models don't necessarily have to have ON symmetry.
Before
Yeah.
you start something new, can I make a question on this?
Yeah, I wanted to also say a few things about it that I've just forgot. Yeah, yeah, say.
The dimension of phi equal to 0.5 in 3 dimensions should correspond to a free field.
Yes, phi becomes a free field in the infinite n limit. But interestingly, phi squared is not a free field. Yeah, it's a funny limit that phi becomes a free field, but phi squared has a huge anomalous dimension. So it's still an interacting conformal field theory, but it's one that we can solve. It's a solvable interacting field theory. Yeah. Any other questions? It's a good question. Thank you. Okay, so what I wanted to say is that just a historical nomenclature. These models are called Landau-Ginzburg models. Landau and Ginzburg did not necessarily consider just the ON version of this. You could imagine, just for the heck of it, that you split the fields phi into 2 groups, and you write the most general interactions that are consistent with ON times OM symmetry. Or you split it to 3 groups. But basically, Landau-Ginzburg models are everything that you can get from scalar fields. That's like a not informal definition. So that's everything that you can just get from scalar fields. Scalar fields. Any kind of phase transition that you can get from scalar fields, you can think about it as a Landau-Ginzburg type transition. It's a huge class of possible phase transitions. And all these things that we talked so far about are in this class. And actually, until recently, people believed that this is all there is, almost. The reason being that, any lattice model that you would imagine would have some kind of phases and symmetry breaking. So you would just introduce the order parameters and make them condense. So there was some kind of idea until maybe 40 years ago that maybe that's all there is. But we'll see it's not true. In any case, anything you can get from scalar fields and just is called the Landau-Ginzburg model. Are there any questions about the classical? Now, this is the end of the classical part. Now I'm moving to the quantum field, to the quantum interpretation of this stuff. Okay. This is much more interesting in my opinion, and also much more modern. So far we had no time. There was no quantum mechanics. It was just some very strange thing where quantum field theory plays a role in classical physics, in classical statistical systems. But there is something that's called it's kind of a overkill. I'm just writing some name so that you can look it up later. There is something that's called the Osterwalder-Schroeder theorem. I mean, you don't really need to know what it is, but I'm just going to tell you qualitatively. Qualitatively, it tells you that if you take a Euclidean structure with correlation functions, conformal field theory maybe, it doesn't have to be a conformal field theory, but any kind of Euclidean quantum field theory that makes sense. You take Euclidean quantum field theory that makes sense, then you do a magic thing, which is t goes to it. Okay, you take all the correlation functions, you do some magic, you do this weak rotation, and you get a consistent quantum system. Meaning, now we have interpretation of time, and we have space, and there is a Hamiltonian, and there is a Hilbert space. And there are operators that act on this Hilbert space, local operators that act on this Hilbert space. And there is Heisenberg's equation for evolution of operators in time. The whole structure of quantum mechanics pops out. There is a Hilbert space, there is a Hamiltonian, there are local operators, there is a unitary evolution, e to the IHT, the whole shebang. So this is the magic. This is the theorem. The theorem guarantees that you get a consistent local quantum system with the whole structure of Hilbert space, by doing this rotation. So even in classical boiling water, there is this funny dual interpretation.
And what if we go in the other sense?
Yeah, it's bidirectional.
No subtlety.
Well, now you said about subtlety, so I'm happy because I just wanted to say that friends of mine have been looking recently at what is behind this thing. When we always we just give them a reference when you write a paper, but people have been deconstructing what they did, and there is nothing there. So the bottom line, I was told that there is nothing there. That they make some assumptions, prove something, but these assumptions are probably not true. So, but I mean, this is probably true. But I was told that there isn't. I mean, that there is no real proof in what they do. There are some hidden assumptions which are probably not true, and they prove something. And then in some special cases, I know that people have been able to fix it. I don't know how far they went. It's probably a true fact, but I cannot say that it's really a theorem. Yeah.
So it's also true if you include buttons.
Yeah, it's supposed to be an extremely general statement with fermions, without fermions. And it also doesn't require the quantum field theory to be UV complete, if you know what I mean. It's also true for effective field theory. In effective field theory, you can probably construct an approximate Hilbert space, approximate time evolution. Everything will become approximate, but there should be a sense in which this is true even for effective field theory. Any questions about it? I'm not going to try, as I said, I have no idea of how the proof goes. And I was told that there isn't a proof, so I'll just mention it as the keyword that if you want to learn about it, that's the keyword. So that means that there should be some way to understand these phase transitions at zero temperature. So far we discussed classical systems at finite temperature. They were described by Poincare invariant D-dimensional quantum field theories. But now we change you should change your mindset completely. Because these finite temperature classical phase transitions, they are driven by thermal fluctuations. Okay, it's all thermal physics. There are classical degrees of freedom and there are thermal fluctuations. But now we change perspective completely. There is not going to be any temperature anymore. We're doing zero temperature quantum mechanics. And the fluctuations are quantum fluctuations. So these are zero temperature quantum fluctuation induced transitions. That's very different from what you might have any intuition about. We're going to talk about quantum systems where h bar is large and there are quantum fluctuations and they cause zero temperature transitions, not finite temperature transitions. And there is a Hamiltonian. So let's start with examples. We should write Hamiltonians on the lattice. I'll start with lattice examples. We write Hamiltonians on the lattice, and then we take some large volume limit, and suddenly we get the same quantum filters, but now there is a Hilbert space interpretation, there is wave function, and blah blah, okay? So it's 0 temperature, d minus 1 space dimensions. Okay, so we should write Hamiltonians that act now on d minus 1 dimensional lattices. So the simplest example is a 2-dimensional lattice that is going to describe eventually, well, that's not the simplest example, but that's the first example. That's going to describe, as you might guess, which model? The Ising model. So we'll now give a quantum 0 temperature perspective on the same 5 to the 4 Landau-Ginzburg transition. Yeah. So we have a 2-dimensional lattice, and we write a Hamiltonian. And the Hamiltonian is called TFIM. This is one of the simplest condensed matter systems. So yeah, in this perspective, we'd say condensed matter. Okay, this is the condensed matter perspective. We have a lattice, we have a Hamiltonian, and we have time evolution, and we have 0 temperature. This is the condensed matter perspective on the subject. And we say condensed matter and not quantum field theory because we're talking about lattice systems here. Okay. So the transverse field, this is called the transverse field Ising model. Transverse field, you'll see why this name's Ising model. It's like a quantum version of the Ising model with some transverse field, and there is a 0 temperature phase transition. So the model is a sum over nearby lattice sites, and it's again ferromagnetic. Now there is no temperature though. And then there is sigma zi, sigma jz, and then there is, how did I call this parameter? H. Sigma ix. These are Pauli matrices. So now the story is completely different. Like all the words are completely different, but many computations end up being the same because it flows to the same fixed point. But all the words and the interpretation are completely different. So you should completely change your mindset now. At every point at every vertex, what do we have? What is the stuff that we have? Before we had at every vertex a binary variable. What is there now at every vertex? A 2-dimensional Hilbert space. What did you say? Yeah, a qubit. They call it a qubit. A 2-dimensional Hilbert space is called a qubit. Okay, so at every point we have a qubit. It's a 2-dimensional Hilbert space. And when I write this is a little bit sloppy. What I mean is that the wave function is now some in the tensor product. So the Hilbert space is just the tensor product of all these Hilbert spaces that sit at every site I. And when I write this, I should really write this, but nobody ever does that, so I'll omit it. It's self-explanatory. So this acts, so there is a 2-dimensional Hilbert space at every point. The total Hilbert space is the tensor product. So you have spin up, spin down, spin up, spin down. So a state could be like this, yeah, where you label the sites in some way. And every sigma acts on a different guy, on a different qubit. Clear? So these are Pauli matrices. These are 2x2 Pauli matrices. And this is also the familiar 2x2 X Pauli matrix. And these are the Z Pauli matrices. And what is the question here? Here, of course, you could try to diagonalize this Hamiltonian. If you are a fan of computers, you can try to go home and verify some of the things that I tell you. You can just try to diagonalize this matrix and verify some things. So before we asked, so what are the questions that we ask? We ask about the ground state wave function. Okay, so the question now is not about finite temperature. We ask about the ground state of this quantum Hamiltonian. We ask about the ground state. Ground state wave function psi. Of course, a more ambitious question would be to try to understand high energy excitations of this Hamiltonian. And that's a fascinating field. There is a huge amount of work on that. I can give you a few keywords if you want to learn about it. You can ask me during the break or later. But the simplest things are about the ground states. I will not discuss the excited states very much. So people are interested in the ground states of such quantum Hamiltonians. That's the first thing you want to know. And the ground state in this system is very interesting as a function of J and H. And I'll argue soon that there is actually a phase transition, as before, as you change these parameters, J and H. Okay, so let's analyze the limit of J huge compared to H. Let's try to guess the wave function in this limit. So actually in this limit it's very easy to find the wave function that's in exact ground state, an exact eigenstate. You cannot do it for generic J and H. Nobody can do it. But for J, for H equals to 0, you can do it. Actually, I can take H to be positive without loss of generality. And J is positive. That's a ferromagnet. Okay? So what is the wave what do you expect the wave function to be in this limit? Everything up. There's another one. Everything down. Right? So you can, the wave function, so all the spins are up. Or all the spins are down. And they seem to be degenerate. So basically the ground state seems to be twofold degenerate. Now let's discuss the opposite limit. Let's discuss the opposite limit. What do you think about the opposite limit? You can also find the exact ground state when J is equal to 0. That's easy. Right. So here the spins are pointing in the x direction. So each spin is... So how does the wave function look? What is the x direction in terms of up and down basis? I think it's like this is the x direction, no? Right? There are two eigenfunctions. This is this. Okay. So we just take this to the power n. So all the spins are in this state, and it's unique. You cannot flip the side. This is unique. That proves that there is some phase transition. So that proves that there is some particular value of J over H where there is a unique ground state. Oh, sorry, where there is a transition between that and that. So there must be some phase phase transition. And it must be a zero temperature phase transition. And people have computed it on the lattice. The value is at 3.3285. People found that when this is the value, there is some very interesting physics that's going on. So what happens at this point? One thing that we didn't say is that this is the ground state wave function, but you can intuitively convince yourself that there are no gapless states. So the Hamiltonian is gapped. At infinite volume, I mean. There are no gapless states, there is a gap. And you can even try to construct at home a mental image of how the excitations look like. They are called magnons. The excitations are called magnons. And it's easy to convince oneself that they have a finite energy over the ground state. Similarly, this ground state is clearly gapped. In order to have a phase transition, which is second order, there is no choice but to have a gapless Hamiltonian. So if the phase transition is second, if the phase transition is second order, which people have shown numerically that it is. So people have shown that a J over H, which is 0.3285. There is a second order phase transition at 0 temperature. This is a 0 temperature phase transition, I emphasize again. And H at infinite volume is gapless. And because it's gapless, what is the correlation length? What is the typical propagation distance if you have a gapless Hamiltonian in quantum mechanics? Infinite. So the correlation length is infinite. But now what the correlation length means is that you ask basically how fast correlation functions in this quantum mechanics are going to decay. And because there are gapless modes, it's not going to decay exponentially. They are going to decay power law. So the correlation length is by definition infinite. And in fact, it's very suggestive because there is one ground state on one side, two ground states on the other side. And is there some Z2 symmetry that's broken? Does anybody see a Z2 symmetry? What is the Z2 symmetry that's broken on this side? Yeah. Yeah, and how does that symmetry, how do you implement this symmetry? There should be a quantum operator. How do you, so indeed, it's basically Z going to minus Z. But you want to preserve sigma x, right? Minus sigma Z. Do you know of a quantum operator that acts on a spin a half particle that does that? Good. So there is Z2 breaking. So of course it's very suggestive that this model will be described by this quantum field theory, the exact same guy that we just talked about. Okay, in 3 dimensions. So now we integrate over 3 dimensions, but we don't think about it as a Euclidean person. We think about it like this. But it's the exact same model, right? So it's the exact same phase transition, the exact same model. Tomorrow we'll start discussing the version of this model where phi is a vector, a 2-dimensional vector. I'll show you how it arises in a quantum 0 temperature phase transition, and we'll start discussing particles, vortices, and monopoles, which are interesting excitations in some such phase transitions. Are there any questions whatsoever about the material we covered today? It's a maybe it's a huge amount of material for those of you who've never seen that, but it is what it is. So, any questions or concerns? Okay. Okay.